Okay, let me just review what we were doing last time and why we're doing it, really. What I was trying to do is I was trying to review perturbation theory by functional techniques. So, and we're doing a specific calculation, but we're heading down a very general path. And the general path is the following, is if I have some Lagrangian that has a free field piece plus an interaction piece, which let's have it depend on phi and phi star like our case here, and I add sources and I want to do a path integral over phi and phi star. It's in general impossible to do explicitly, directly, because of that interaction piece. It generally prevents you from doing it because all you know how to do in the world is Gaussian integrals. So we do a trick. We write this as integral d for y, L interaction phi and phi star. Separate that out. E to the I integral d for x, L0 plus j phi plus j star phi star. The stuff on the right there we would know how to do. The stuff I've pulled out is the problem. This is allowable in this case here. It's in path integral because these are just numbers, so they're not operators. You don't have to worry about ordering or anything like that. So there's no commutation stuff, just numbers. The trick then is you write this, there was an I there, sorry, integral d for y, Li of minus I delta delta j minus I delta delta j star e to the I integral d for x, L0 plus j phi plus j star phi star. So it's the functional trick that variation with respect to j gives you phi when you're acting on that guy. So so that you now no longer have phi there. All you have is what's left there. And so our path integral can be done. We get integral d phi star e to the I integral d for x, L0 plus Li plus j phi plus j star phi star. We do this trick. We pull the interaction piece out. It sits out in front, e to the I integral d for y, Li of the variational and then you do the rest of the path integral, which is just a number, e to the I integral d for y, or let's make it x, d for y, d for z, sorry, j star of x, df x minus z, j star of z. Okay. I know star at the end there, right? Okay. So we've done the path integral, and now anytime you see this interaction piece, you just bring down factors of the propagators, so everything just comes out. So in this case, we can there's no external phi particles. And so we set J is equal to 0 after differentiation. Because there's no matrix elements involving phi's, so we don't have any external derivatives with respect to J. And what that then does is that delta J, delta J star always turns into IDF of whatever the integral. So it turns into propagators in pairs. And so all you end up with is various propagators sitting in places. Okay. So if we're doing our particular problem here, so propagator factors, we get if the Li is E squared a mu phi star phi, that turns into E squared a mu I df of y minus y, so that's this variable is y. It turns into something that looks like that. And in the other case, the other term we had at next order, we had d4y minus IE a mu phi star d mu phi plus another term. I'm only going to use one term here, and then integral d4z minus IE a nu phi star d mu phi d nu phi, sorry, with another term. This is the current one, so this is at two different locations. That turns into, there's an a mu of y, a nu of z. Turns into some things that look like derivative mu respect to y of df y minus z, and d nu with respect to z of df of z minus y, things like that, okay, plus other terms. Okay, and that then turns into things that look like that. And remember, disconnected diagrams drop out in the end, so they don't contribute things that go like that. There are no contributions like that, really. Okay, so that's basically what we're doing. Let me just finish. We then, having done that propagator, we have the full propagator. I mean the full generating functional J mu. It still has the dA mu left over. Then there's this perturbative correction, which at this stage looks like the following: d4y e squared a mu I df y minus y. We just addressed that piece. And then there's a minus a half integral d4y d4z minus I a mu of y. There's a minus IE. Minus IE a nu of z, and then factors that look like d mu df of y minus z d nu df of z minus y, plus three other terms. Okay, and all this gets still multiplied by the part that depends on a, which is e to the I integral d4x minus a quarter f mu nu minus j mu a mu. Okay, so it's a little painful, but there's all these terms. This is the piece that was the free field case, just the photon. This would give the usual propagator, and these are the corrections. And then again, you use the trick that, use the functional trick that the A that sits in the various places there, you know, a mu of y, e to the I stuff is I delta delta j mu of y, e to the I stuff. And so then you can, you again convert this to delta delta j's, these guys there, you do the integral, and the end result is z of j mu equals 1 plus I integral d for y, things like e squared df y minus y delta delta j mu of y delta delta j mu of y plus lots of other stuff, z0 of j mu. Okay, so that's the free field case. Okay, and then finally we have the propagator g2 of x1 x2 is gotten from this by taking minus I delta z of j one over z0, and then at the end of that you finally said j is equal to 0. Okay. And at this stage I'm not there's I can write it out if people want, if people are not seeing through what we're doing, but basically again all the j's have to end up being propagators in pairs, so there's some external propagators, some external functional differentiations. This is x2. Some internal ones, and the end result is that for the piece with a 1 there, you get a single propagator, which is this guy. For this term here, there's propagators here that can be paired up. So there's 2 propagators total, because there's 4 derivatives. Each pair brings down a propagator, and it turns into the one where there's a propagator, this vertex, another propagator. So this is the point y here, and then the other pieces turn into the rest of perturbation theory. There's also ones like that. Okay. Yes.
Just another notation. Are there indexes in the
So yes, thank you. This is mu and nu because it's a photon propagator. So the first piece here is I df mu nu of x1. And again, I can write out these next terms here. The next term will have a df of x1 minus y, df, that's a photon propagator with two indices. So mu lambda, this propagator there, then another one lambda to nu, the external propagator. Okay, so that's the way that we develop perturbation theory using these functional techniques. This was really meant as a review. What I really want to do is this next way of doing it. But let me take any questions that you want to give at this stage. Any others besides the notation one? People follow that okay? All right. So what I'd like to do now is do the path integral to make sense of it a completely different way. So forget about this functional differentiation for the moment. At the end, we'll still do a little bit of it. But here, I'm going to be interested in, I'm going to use the following. Use that the integral d phi, well, the basic formula that we have is e to the I integral d for x 1/2 phi o phi equals some number times the determinant of O to the minus a half. Okay, that's the other integral formula. So if you remember when we first started doing this Gaussian integral, the finite dimensional Gaussian integral, we started by doing that one and you get the determinant. And so my goal here is to do the path integral using this and then show you how we make sense out of this crazy thing, the determinant of a differential operator. So that's our goal here. Okay. So again, we're doing the same calculation. And in fact, the calculation works a little easier here. So we're going to do the vacuum polarization. And we have z, again, j mu j equals integral dA, d phi star, e to the I integral d4x, L0 plus Li plus j mu a mu plus j phi plus j star phi. That's our starting point. But again, like I said somewhat before, here there's no external phi states. And so you can set j is equal to 0. The last time I didn't do that because I needed it to do perturbation theory. I needed this functional derivative with respect to j to do perturbation theory. But since I'm not taking that path now, I can just set it equal to 0 now. So you can forget about those guys. And the photon sits in the external state, so we'll keep that one, but it's just going to be a traveler. It's a fellow traveler. It's just going to come along for the ride. So what we're going to do is we're going to do leave the A integration and let that be as usual, integral d4x minus a quarter f squared plus j mu a mu. And what we're going to focus on is d phi star e to the I the Lagrangian that's a function of phi star and A, and we're going to do this. So at this stage, this is the idea of integrating out the field phi and phi star. So the phrase is we're going to integrate it out, and we're left over with something which we'll call e to the I w of A. Okay, phi and phi star are gone. The only thing that's left that can depend on is A, and so our overall path integral will have this piece and then the w of A. We'll see a couple things that come out of this. One is we'll see the same old vacuum polarization diagram fall out. We'll also see how this piece leads to the renormalization, wave function renormalization of f squared. So we'll do wave function renormalization this way. And finally, we'll see when we can use an effective Lagrangian description of this term to just add a new piece to the Lagrangian, and when that's not a useful idea. Okay, so lots of things come out here. Okay, fair. So the place where we're going to start is I'm going to write the Lagrangian of phi star in A. Okay, it's just phi d mu phi star capital D mu phi minus m squared phi star phi. I want to write that in this form, phi star operator phi. So the first thing to do is to put it in standard form. To do that, let's write out this first term here. The d mu phi is d mu plus I e will be the charge a mu acting on phi. On the other side, we complex conjugate everything. So it's d mu minus I e a mu acting on phi star. So then I get minus m squared phi star phi. Okay. This sits under the integration sign, so I can take this derivative that's acting on this and integrate by parts. Okay. That if I integrate it by parts, it flips it over and it acts on this whole thing. So this turns into, there's a minus sign from that. Phi star sits over here. It becomes d mu plus I e a mu acting on d mu plus I e a mu, both acting on phi. Okay, so this minus sign here is that minus sign times that sign there. The extra change here from here to here is the integration by parts change. Minus m squared phi star phi. So this overall is minus phi star d mu plus m squared phi. Okay. So we again end up with covariant derivatives. It's just covariant derivative squared. And so this is then minus phi star, our differential operator, phi. Okay. The path integral that we want then is integral d phi star e to the minus I integral d4 x phi star d squared plus m squared phi. So this turns into the determinant of d squared plus m squared to the minus 1 power. Okay. Now, the one thing I did do, which I haven't re-derived for you, but this one, the basic integral that we started off with has minus a half power, but there's two integrals here, phi and phi star. And so if you think of it as two real fields, you get each one. Let's forget the covariant piece. It's just derivative plus m squared. They're the same, so this becomes 1/2 phi 1 plus 1/2 phi 2. You have this becomes d phi 1 d phi 2. You get two of them. So for a complex scalar field, you get this minus 1, so it's minus a half times minus a half. It's the same thing. So it's not minus a half, it's minus 1. Okay? Anyone want to see that in more detail? It's just okay. It's just there's two fields, and so each of them gives d squared plus m squared. The product of two determinants is then to the minus a half, it's to the minus 1 power. Okay. So there's our answer. This is what we called e to the I w of a. And it's a function of a. But what function? So that's the real purpose of this section, at least the first part of it, is to make sense out of this extremely formal object in terms of real functions that you can put your hands on. So the key identity here is the determinant of some operator is e to the trace log of the operator. All right. That doesn't seem like it's going to buy us much, but let's just do it. But first, so to prove this, the easiest way to prove it is you diagonalize O. That's okay. That leaves the determinant unchanged. So d O diagonal is determinant of O. So they have the same determinant. But we know how to calculate the determinant of the diagonal one. It's then just the product and of the eigenvalues of O. Okay, so when you diagonalize it, you got diagonal, you take the determinant, it's just the product on the diagonal of all the eigenvalues. Okay, then if I take e to the trace log O diagonal, that's e to the sum over the eigenvalues of log of the eigenvalues because of the product of the properties of the exponential. This is the product of overall n of e to the log lambda n, which is then the product of all n lambda n, which is then the determinant. So we can take the determinant and write it in this fancy form of e to the trace log. What does trace mean? Okay, log just means log. We're stuck with that. Trace, remember, when we're talking about this differential operator, each element is isomorphic to a point in space-time. So remember, when we had the matrix element e to the I, let's call it yi a ij, yj, this went over, y turned into e to the I d4x, phi of x, some operator, phi of x. So the indices on this operator are space-time. So when I say trace log O, what that implies is it's the integral d3x, the x matrix element, the diagonal matrix element, and it's d4x, of course. Okay, so using that identity, if I have the determinant of d squared plus m squared minus 1 as my answer, this is e to the I, no, there's no I here, sorry, e to the integral d4x. There's a minus sign from the minus 1. X log d squared plus m squared x. Okay, so it still looks a little formidable, but it's a little bit better. Okay, if I asked you to calculate the determinant of d squared plus m squared, that the determinant is over all positions in space-time. That's a very nasty beast. This is only slightly nasty, right? This is something that we could imagine doing, taking some integral over x of some function, and we just have to figure out what the function is. Okay. There are techniques for making sense of what that is in some cases exactly. So there are some cases. For example, you can do it in a constant electric field. You write out what d squared is as a function in a constant electric field, and you can make sense of it. And the classic reference on that is some work in, I think it's 1951 by Julian Schwinger, where one of the calculations there is it's this classic calculation where the constant electric field, you can write out the generating functional basically of a constant electric field allowing fermions to exist. And what you find is that this picks up, it's exponentially suppressed, and it picks up an imaginary part which says that if you have a constant electric field, that situation decays by producing its pair production, basically. So a constant electric field, you can produce electron-positron pair and let the electric field decay. So, but anyway, there's a few cases with special fields where you can solve that. What we're doing is perturbation theory, and that's aside from the special cases, that's what you have to do. So here in perturbation theory, we will treat this in a different way. So perturbation theory. So that's the correct answer, and that's it. But this is a better pathway through it. Let's let O0 be just the free field case, D'Alembert plus m squared. And let's write d squared plus m squared is D'Alembert plus m squared plus some interaction piece. Okay. We can write that formally as O times O minus 1, O0, O minus 1, times d squared plus m squared, which is then O0, 1 plus O0 minus 1 V. Okay. D squared plus m squared is O plus V. So O minus 1 on the O piece is the 1. O minus 1 is this. Okay. So what's O minus 1? That's O minus 1 is the propagator. Okay. O0 is the del squared plus m squared. The thing that inverts that is the propagator. So let's just leave the indices off at the moment. We'll make sense of them in a minute. So then the determinant of d squared plus m squared is the determinant of O0 times the determinant of 1 plus O minus 1 V, O0 minus 1, which I should write that as df at this stage since I've got it there. Okay. Determinant of O0 is just a number. It has no A dependence. So we'll write that as a number. Determinant 1 plus dfv. So now we use this trick, write this as a number e to the minus integral d4x, x matrix element of 1 plus df, I'm sorry, log 1 plus dfv. All right, it doesn't look like we've done too much at this stage because this looks just as formidable as this, but it's even worse because that's the inverse operator. Okay? But at this stage, perturbation theory comes to our rescue, and we'll get rid of the log because this, if this interaction piece is small, we can Taylor expand that, and you get rid of the log. So log of the differential operator is not there anymore, and we just get things that are going to be powers of df times v, and we can make sense of that. Okay. So let's do that. So this is then n e to the minus I integral d4x. Well, the first piece is then x df v x. The second piece is a half x df v df v x, and keep going, of course. So we're getting there. Okay, this is still looks a little formal, but at least we don't have that log anymore.
What's the assumption that you make in order to do the extension?
That we're doing perturbation theory, that v is in some sense small. Okay, so remember, in our case, the derivative has a factor of the electric charge in it, EA, and so this is of order E in order E squared in it. So if we're doing perturbation theory in E, this is small compared to that. Okay. And that's why perturbation theory is the easiest way to evaluate this. If you had to evaluate that altogether, it's painful. But in perturbation theory, it's not so painful because by this trick, you can expand the log, and you get stuff that's not too bad. Okay. So our last task is really just understanding what these terms mean and turning them into real functions that you can get your hands on and deal with. Okay. This one. Minus 1, yes, thank you. Thank you, yes. So I still have the minus 1 here, and that turns into that minus 1 there. Okay, so there's a minus sign there. Yes, thank you. And, well, actually, yes, so let's put minus 1s all over these places here. Okay, so they belong everywhere along the line. Thank you. Okay, let's do it. The piece we had then, you remember, d squared was equal to del squared plus let's see, there's a plus IE a mu d mu, and then there's a plus IE d mu a mu, and then there's a minus e squared a mu. Okay, right? And this is acting on phi, was acting on phi. Now it's just a beast by itself. Okay, so this is what we called V. The piece I'm going to be looking for, I'm going to be looking for terms of order E squared. Because that's the vacuum polarization piece. And terms of order E don't vanish for other reasons. So when I take x df v x, this has the following pieces of order E squared. There's the minus E squared a mu evaluated at x times df of x minus x. Okay, so a mu is diagonal. So this x on V just gives this a mu, and then the x matrix element of df is df of x minus x. Okay. This converts into the diagram that we saw that was like that. The second order piece, back here we had this piece, so there's the order e squared piece, and there's a piece here too. So if I'm trying to interpret x df v, let me keep this df v x. Okay. That's not necessarily diagonal because df is not. So the easiest way to interpret this is to put a complete set of states here, d for y, y, y. This converts then into the term that's of order e squared here has an a, and so it's integral d for y df of x minus y a mu d mu plus d mu a mu df of y minus x, and I have a mu d mu plus d mu. I have to do a different index. Lambda, 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 lambda. One of these is, let's see, this one is y, and this one is x. Okay. So now these are now functions. The result that you get then has this turns into the piece where you have derivatives acting on the propagators. You can sort of see the factors that come out in perturbation theory also come out here. If this guy has e to the I k dot x, and a in the end will go like e to the I q dot x, then this piece is k, this piece derivative acts on a and on d, so this term, this whole set of terms here turns into something that looks like 2k plus q mu, which is the piece that comes into the Feynman rule. Okay, so these terms then behave just like the vacuum polarization function, so that we end up with something that looks like e to the I w of a is e to the I, so that's an integral d for x df x minus x a mu x, a mu of x from the first piece, and then there's a minus a half integral d for x, d for y. It's e d mu a mu plus a mu d mu at x df x minus y times e d lambda a lambda plus a lambda d lambda at y df of y minus x. Okay, so we're back actually where we were before. We've gotten the rules out. The last time, the only difference was that we had integrated this derivative by parts, so it acted on the d, but in this here it acts on d, so that there was it was a slightly different form, but numeric-wise it was the same, and so we end up with the usual that plus that calculation. Okay. People follow that enough to buy it? Okay, we want you to. The purpose of this was making sense of this funny beast determinant of d squared plus m squared, because we're going to end up using that. And here we make sense of it in perturbation theory, and it turns into normal functions and just regular stuff. Yes.
I just have one question. Just above there, where you had dfv.
Yes.
And you said that's diagonal, and then below that you needed to introduce a complete set of
Yes.
shapes, and that wasn't diagonal.
Yeah. Well, see, yes. So df is not diagonal. You know.
In what sense is it not diagonal?
Well, it's okay.
Or, like, what does that mean?
Yes. So what does it mean? Good. It's a good question. Good. So v is just a function of x, right? So if you, but the propagator takes you from x to y. So to invert this differential operator, remember the operator is a differential operator. Its inverse is this Green's function, which is a function of these two points. So when you hit this, it can take you to a different point. And so by putting this complete set in here, I've done that. If I had put a complete set in here, I could have put a complete set in there too. And the first piece would look like I'd have something off diagonal. But this piece, the y v x matrix element is a delta function of x minus y. Okay, because it's only just a function of x. There's no y dependence. Okay, so that would have killed that, and so I didn't need to do it. Okay. Remember the so a differential operator is in some sense a function of two different points, because when you try to make sense of the differential operator, you take x and x plus delta x, and then you take this limiting case. So its inverse is also non-local. Okay, does that make sense? You okay on that? Yes.
Question. What's the connection with the effective, like the W
Right.
and the functional generator? Because if you take the ln now of everything, is this the same as taking the functional derivative with the source?
Well,
you get the same.
Okay, so what we would now do, let me try to answer that by a formula. We now have z of j is integral d a e to the I integral d for x minus a quarter f squared plus j mu a mu times e to the I w of a. Okay, so this is a function of j mu. If I wanted to now look at the effect of vacuum polarization, I append that functional that I have there to the original one that I have and I'm going to do that now in just a minute, just by in a particular case. I don't take the log of that at this stage, because it still sits inside this path integral here, so I have to do that path integral somehow. And so, at this stage I could turn to perturbation theory, and I know that's a function that's expandable in powers of E, and I go back and do basically the same thing I did in the functional example, since I've now reduced this to basically the same form. Does that answer your question enough? Okay, good. Okay, so what I'd like actually now to do is to try to make sense of this as an addition to that. In a sense, we almost had it there. And so the heading of this will be sort of renormalization and the effect of Lagrangian. Okay. So at this stage, I have to recall for you the answers. I'm going to work first in the case of a large mass for the field phi, and we had pi. So the Feynman diagram calculation, pi mu nu of q squared was q mu q nu minus g mu nu q squared pi of q squared, with pi of q squared is some constant pi of 0 plus alpha over 60 pi q squared over m squared. Okay. Now, in matrix elements, if I have I d lambda, that turns into q lambda. But the equivalent result of that is that the q's that you get here could be written as derivatives on fields in coordinate space. So that I could write e to the I w of A as in the following form to get the same result. I get e to the I integral d for x. I could write a mu d mu d nu minus g mu nu box a nu times pi of 0. So the constant piece here, this reproduces that. And the second piece would be minus alpha over, there's actually a half here, I'm sorry. Alpha over 120 pi a mu, again this d mu d nu plus minus g mu nu box, but now because there's q squared, there's an extra box over m squared a nu. Okay. So the two terms that you get in momentum space here are equivalent to just writing this Lagrangian out in coordinate space. When I differentiate and in Fourier transform, I reproduce this. Okay? Everyone buy that? That's an important piece. So in this case, I've written W of A in a particularly simple form. You can actually get there directly in coordinate space if you really need to. It's a bit painful. It's easier to have done this calculation, but you can go back and do this set of things and write these derivatives on df's in such a way that you end up with derivatives on a. Okay, it's a painful manipulation, but it's easy having done the calculation in one space to write it out. Okay, so now let's go back and take this and append it to that. Now we have a Lagrangian here that's a function of x. We're adding to it new terms in the Lagrangian that have that piece, those forms. So overall, at this stage, let me try to finish the lesson by redoing the part that occurred after the computer froze up. To proceed, we're going to make note of the fact that if you have half a mu down version d mu a nu that's something that we showed a while ago. It was equivalent after integration by parts to minus a quarter f mu nu. So the derivatives work out so that it looks like f squared, and the minus sign comes from the integration by parts. So the overall, what we had before, the generating functional can be written in the form integral dA e to the I excuse me, integral d4 x minus a quarter f mu nu 1 minus pi of 0. So the pi of 0 from the vacuum polarization looks just like f squared. And then the other piece, if I have my numbers right, is 1 over 120 pi f mu nu D'Alembert f mu nu. So D'Alembert over m squared. So the q squared over m squared piece, the extra q squared turns into an extra D'Alembert. And this then is our total path integral. There are two results that you can see from this. One is the renormalization. If we take our field A and change its normalization, AR, by a factor of z3 to the 1/2, with z3 equaling 1 over 1 minus pi of 0. So you substitute that in back up there. The z3 that comes out from there's two a's cancels the 1 minus pi of zeros, and we're back to the usual normalization. In dA, the path integral, that just shifts it by a number, dA renormalized, so that which drops out when you take matrix elements. So this shows you that normalization doesn't play any role, but here we can just make it conventionally normalized by making that choice of variables. The second thing that we see out of this is that there's an effect of Lagrangian. The effect of Lagrangian is the minus 1 over 120 pi F mu nu derivation over m squared F mu nu. And that contains the information of the heavy field. It's been integrated out. This is its residual effect at low energy. And it wouldn't normally be included because it's a higher dimension operator. The operator is dimension 6, has a coupling constant suppressed like 1 over the m squared. But nevertheless, it's the residual effect of the heavy particle. The way you'd use this in perturbation theory you take this Lagrangian, you read out the Feynman rules. There'd be a new Feynman rule, which would be basically put a little x there. That x ends up being the minus I alpha over 60 pi q squared over m squared q mu q nu minus g mu nu q squared as before. So that's just the vacuum polarization, and you'd use that in a Feynman diagram where, let's say, you're doing some scattering, some other particle. You'd put that in there. First term would give you the usual piece. The second term, after a little massaging, gives you the Lamb shift, or a contribution to the Lamb shift, just like we did back when we did the vacuum polarization. So the residual effects here end up being equivalent to what's called the Perturbation theorem. Perturbation theorem says that the effects of the heavy fields go into one renormalization constants or to the suppressed by powers of the mass. To some power. In this case, it's 2. And so we've included all the effects of the heavy mass, heavy particle in this simple effect of Lagrangian. But I do want to point out that it only happens if it's heavy. If m squared is much less than q squared, so it's very light, you cannot use the effect of Lagrangian. And this you can see in pi of q squared has a piece which is minus alpha over 12 pi log of q squared over m squared. It's minus q squared over m squared actually. And there are 2 problems with this. One problem is log of D'Alembert, if we convert this to a momentum space, is not well defined. And the other is that if I take log minus q squared, that's log of q squared plus I pi, if q squared, that's theta of q squared. So if q squared is greater than 0, log of minus a number picks up an I pi, and an effective Lagrangian has to be real. So this just goes into the issue of how you can define these things. And so you can't define an effective Lagrangian, you can't define log del squared in any sensible way because of these problems. There's a physical reason. The physical reason is that for the heavy mass, all the effects are local. So things like the vacuum polarization is local, meaning the heavy mass can't propagate very far, so you can write it in a Taylor expansion about the local point. And so that lets you write out a local effective Lagrangian. If the mass is light, then in this propagation, that the propagators can go very far, it's not local, implies there's no local effective Lagrangian. So it's this locality issue that allows us to define this. All right, let's stop there.